It is section 9.2, Neural Networks. In this section, we'll see how neural networks are organized, and we'll consider a network example for the classification of handwritten digits. Let's begin with a recall for the perceptron algorithm. For input values x, the algorithm is trained to learn weight vector. And once that input is obtained, this is the weighting of evidence. And by using the activation function of a threshold, it can be classified. This 9.1, equation 9.1, can be written equivalently in this way. Rather than some value theta, that can be moved to the other side. And now b, which is minus theta, is the bias. So that along with this thresholding, the classification, the prediction can be done. The perceptron algorithm can be illustrated in this way. As in the picture, the input values are now weighted up, and then for the value, by using thresholding, here prediction is made. Perceptron is the simplest artificial neuron. It makes decisions by weighting up evidence. However, it's not a complete model for decision making. It is too simple. Now, for complex networks, we can use the perceptron as a building block so that we can make more complicated, complex networks. Okay, here. Now, if we look at each neuron unit in a layer, then this, the weighting up is exactly a kind of the perceptron. And these are stacked, and we get this complex the network. Okay, for this one, and now this is beginning is input layer, and the last one is called output layer, and between them we call them hidden layers. Okay. Now, along with a complex network of a perceptron, we can make a quite subtle, delicate decisions. Okay. Here we have an issue on perceptual networks. The problem is thresholding, so that small change can make the value from -1 to 1, so that it's not really stable in some sense. So that to make it differentiable and stable, and we may try to use some other the activation function. For example, sigmoid function can be used to get sigmoid neuron. Okay, we'll see here the detail. Now, earlier we studied about logistic sigmoid function defined as in this equation, so that pictorially the output of the sigmoid function is between 0 and 1. Now, here the sigmoid function is given in this form applied for the net input. And here, but this function is differentiable. Not only continuous, but it's also differentiable. And then the derivative is well known in this range. And the sigma derivative same as sigma times 1 minus sigma. So that here the small change in weights and bias produce corresponding small change in the output, so that we can use the calculus technique and smooth and also the differentiable, and in a sense this activation is stable, so that by using the sigmoid function rather than threshold, the system can be much more stable. And now we can use also calculus technique to get the learning rule. Okay. Here we summarize that the architecture of smooth neural networks. The leftmost layer is called input layer, and then the neuron within the layer is called input neurons. And rightmost layer is called the output layer, and middle layers are called the hidden layers. The design of the input and output layers in a network is quite straightforward in many cases. And here, for example, when we are dealing with hand-written digits, then because the images are in 28 by 28 grayscale pixels, we can set the 28 squared, which is 784 neurons in the input layer. For output layer, and because it's classifying 10 digits, so that we can set 10 neurons in the output layer. Here, rather than 4 means that once you are considering the binary classifier, then now here, if you put together 4 of them, then each one has 0, 1, so that the total number of different output can be 16, so that you may try to use 4. You can do it. And however, in practical simulation, and setting 10 neurons in the output layer is much better. And we'll see how we are making the output layer. In fact, it is related with one hot encoding. We'll see later on the detail. And there can be quite an art to the design of hidden layers. It's not easy to say by using a few simple rules of thumb. And here researchers have developed many design heuristics along with the heuristics, and here one can determine how to trade off the number of hidden layers against the accuracy and the time required to train the network. And it's not easy to say, not easy to summarize the rules of thumb. However, the heuristics can be used as a guideline to design the network having certain number of hidden layers and certain number of units and so on. Okay, that's the end of the part 1. We'll continue in the second part.